Okay, we're moving on to section 2.2, and in this section we'll be talking about symmetry. So basically in this video, we want to figure out what it means to be symmetric with respect to either the x-axis or the y-axis. So as a first example, we'll consider the graph of f of x equals the absolute value of x. Hopefully, most people remember that it just looks like a V shape. Since on the right-hand side, when we plug in x, we just get back x. On the left-hand side, when we plug in a negative value of x, it just gets flipped up to the positive value. And so in this graph, we notice that if we fold one side over onto the other, so we fold it across the y-axis, then the graph looks exactly the same. So this is what's known as y-axis symmetry, meaning that across the y-axis, it looks exactly the same, just a reflection. And there's actually a mathematical way to check this, to check if a picture has y-axis symmetry. And that's described down here, that if xy is on the graph, then so is the point negative x, negative y. So for in our case, we see that if we have 3, then this point here is 3, 3. And at negative 3, the absolute value of negative 3 is 3. So therefore, this point is negative 3, 3. So it passes the test. We have 3, 3 on the graph, and we also have negative 3, 3 on the graph. Now we'll do a quick example of x-axis symmetry. It's basically the exact same idea, except now we have, now we're doing it across the x-axis. So let me just draw a picture. We can have some graph of some function look like this. And this picture is going to admit x-axis symmetry. Since we fold the graph across the x-axis, it looks exactly the same. And we can always do a similar check as well, where in this case, if we have xy on the graph, then so is x comma negative y. All right, so for an example, we want to show that the graph of x squared plus 12 has y-axis symmetry. So we know we have y-axis symmetry if xy on graph implies minus xy is on the graph. And so we'll say, let x naught, y naught be on the graph. So we want to make sure we're doing this without making any assumptions on what x naught and y naught are besides just being on the graph. And so then we can just plug in negative x naught squared plus 12 equals, well, that's just going to be x naught squared plus 12, since the negative just squares out to a positive, and that's going to be y naught. So that tells us that we have negative x naught, y naught on the graph, Therefore, it has y-axis symmetry. Now we're going to jump into something we haven't talked about before. That's a circle. So you remember that the graph of a circle, that this equation defines the graph of a circle where 36 is our r squared. So it's our radius squared. So we have a circle with radius 6, centered at the origin, and we want to show that it has x and y-axis symmetry. So first we say x naught, y naught is on the graph. And then check negative x naught, y naught. So we just plug it in and we get negative x naught squared plus y naught squared equals x naught squared plus y naught squared. And since x naught comma y naught is on the graph, that tells us that this also has to be on the graph, so that has to be 36. So therefore, we know we have y-axis symmetry. And we also check x naught negative y naught. And by the same computation, almost the same computation, we get x naught squared plus y naught squared, and that equals 36. And so that gets us x-axis symmetry. And just looking at the picture, we should be able to see too that it has x-axis and y-axis symmetry. And then we have a bonus problem. This is the graph of this is the equation that defines the graph of an ellipse. And that gives us an ellipse that looks like this, where the x-intercepts at 1/2, and the y-intercepts at 1/5. But I'll leave this problem for you guys to do. All right, so that's it for now on symmetry across the x-axis and y-axis, but I will have one more video on symmetry about the origin.